So in this question we read, a system of light springs that does not obey Hooke's law has an unstretched length of 2 meters. The extension of the system is related to the force applied to it by F equals px squared, where p is a constant. A force of 2,400 newtons increases the length of the system to 2.2 meters. So immediately I'll use this information to write 2,400 newtons is equal p times 0.2 squared. How much work is done in increasing the length of the system from 3 meters to 4 meters? Well, this force keeps changing with extension, so we can't just apply work done is force times distance moved blindly. So how do we approach something like this where the force keeps changing with position or displacement? Well, what we do is we break this down into infinitesimal changes in the extension. So what do we mean by that? Well, the little bit of work done in a small change in extension would be the force at that extension, x, times the little change in extension, dx. Because the force keeps changing, so if we break this down into finer and finer slices, we could approximately get the work done is equal to this. And then the smaller we make that interval, the more accurate this becomes. You might have seen this in school as saying, when you have a force times extension graph like this, so I've just drawn an arbitrary one here, then the work done is equal to the area under this graph. But what we're really doing is we're saying that we know work done is usually force times distance when the force is a constant. So what we're doing is we're breaking this down into very, very thin sections. So I'm drawing a very thin rectangle here, where the width or thickness of that rectangle is dx, the change in the extension. But we know the force in that interval is roughly constant. It will be roughly f of x. Like that. So the larger you make those intervals, the less accurate your answer is as an approximation. The finer or thinner you make them, the closer and closer you get to the true answer. So your approximation becomes exact as you make the thickness approach 0. So we got the little work done in this section equals f of x times dx. So how do we get the total work done between 3 meters to 4 meters? Well, we'll need to sum up these little bits of work done. So we'll need to sum, i.e. integrate these little bits of work done, which is sum of p of x squared times dx, the change in the extension. So now we need to look at the limits of this integral. Well, we're going from 3 meters to 4 meters, and the unstretched length is 2 meters. So that means at 3 meters, our extension is already x equals 1 meter. And then at 4 meters, our new extension will be x equals 2. So we're just looking at the work done in stretching it from 3, where it's already extended, to an extension of 2 meters, i.e. to a new length of 4. So integrating this, what do we get? Well, we'll get p over 3, and then we'll get x cubed, which we then substitute as 2 cubed minus 1 cubed. Now writing this, we can see that this is p over 3 times 7, and substituting our expression for p above, we knew 2,400 equals p times 0.2 squared. So notice I haven't actually worked out what p is yet, because I know if I substitute now, I should get some cancellations. This is a common trick in the NSAA. So I'll use 2,400 over 0.2 squared times that 3 that we already have there, times 7. Cancelling some things out, we have 800. We cancel the 3 and 2,400. And then we have times 7. And then I'll write this as 2 times 10 to the minus 1 squared. because usually in the NSAA, you don't want to work in decimals, I should say. So we try to get things in either fractions to look for cancellations or powers of 10, i.e. standard form. This makes calculations or arithmetic quite a bit easier. So simplifying this, we should get 800 times 7 over 4 times 10 to the minus 2. If you notice 800 over 4, we should get 200. Times 7 is 1400, and then with another 2 zeros, we should get 1400 with another 2 zeros and joules. Now, what answer is that? You notice that's either 140 kilojoules or 14 times 10 to the 4 or 1.4 times 10 to the 5 joules. So the relevant answer here is E, 140 kilojoules. So that is the amount of work done in stretching or increasing the length of the system from 3 meters to 4 meters.